In the 21st century, humanity has many problems that it faces long term. One of the most formidable is climate change, which is driven largely in part from pollution in the air from burning fuel in cars. There are several alternatives to burning petroleum that are slightly better for the environment. One such alternative is biodiesel. Biodiesel is a diesel fuel substitute made from used free VAT oil that eliminates or minimizes the problems with using vegetable oil as a motor fuel, but maintains many of the environmental benefits. Biodiesel will not turn rancid due to bacterial action when it is in storage, but when it is spilled in soil, the combination of soil microbes and moisture causes it to biodegrade rapidly. Biodiesel has been proven to have 10% reduced carbon monoxide emissions, 15% reduced particulate emissions, 10% reduced hydrocarbon emissions, 20% reduced sulfate emissions when compared to diesel, so it is clearly better for the environment. Both fuels produce carbon dioxide as a byproduct of combustion, but the process of growing plants to produce vegetable oil, which is used to produce biodiesel, removes carbon dioxide from the air. The end result is that producing and using biodiesel releases about 50 to 78% less carbon dioxide than producing and using petroleum diesel. However, biodiesel also has certain disadvantages when compared to alternate forms of energy. The most serious problem preventing widespread use of biodiesel is our limited capacity for producing vegetable oil. If we grew enough vegetable oil producing crops to satisfy all of our fuel needs, there would not be enough arable land left for food production. Additionally, at temperatures below a threshold called the cloud point, biodiesel forms wax crystals that can restrict the flow in a vehicle system, clogging fuel lines and filters. Thus, to mitigate concerns and take advantage of biodiesel, blends of biodiesel and petroleum are used.
In this experiment, we would create blends of petroleum and biodiesel in various combinations and would like to observe what effect varying the ratio of petroleum and biodiesel have on the blend's heat of combustion and the temperature at which the blend reaches its cloud point. First, we are going to synthesize biodiesel from vegetable oil through a process called transesterification, which converts oils and fats of natural origin into fatty acid methyl esters, also called FAME. In this reaction, the alkoxy group of one ester is exchanged with that of an alcohol to form the desired ester product. Next, we will create our blends. We will create 4 blends in which the concentration of biodiesel will vary from 0 to 100%. After creating our blends, we will test them for their heat of combustion and their cloud point. Each blend will have 3 trials for the 2 readings. To test the heat of enthalpy, a bomb calorimeter will be used. To test the cloud point of our blend, we will use the ASTM D2500 procedure, which is the standard to measure cloud points. The sample will be cooled down from room temperature using a water bath and will be inspected for wax crystal formation at 1 degree Celsius drops in temperature. Then our data will be analyzed and the mean, standard deviation, and the uncertainty at a 95% confidence interval for each blend will be calculated. We will create graphs of heat of enthalpy and cloud point versus the ratio of biodiesel in the blend. Lastly, we will analyze data to compare each blend with petroleum in terms of energy content and cloud point. The blends which maximize energy content and minimize cloud points can then be chosen. We hypothesize that biodiesel will have a heat of enthalpy that is greater than or very close to that of petroleum. This value should decrease as the ratio of petroleum in the blend increases. We suspect the same to be true for the cloud point. The cloud point of a pure biodiesel should be the highest and it should decrease as the ratio of petroleum in the blend increases.